essentially, we started by rationalizing the importance of the topic. Why are we interested in the layout problem and in finding a good solution to the layout problem? And I have mentioned one aspect of that, which is when we come to determining the process charts and process flow times, one of the things we look at are the distances traveled and the times taken. So, as a result of that, we said that we need to take into account this while designing a layout for a facility. And to do that, we start by, specifying the locations or the slots and assigning the various departments or the various units to those slots. Our objective is to find the design, is to find the layout that minimizes our evaluation criteria, which in our case, we're basing it on the distances traveled. Now, just to reiterate, okay, and so that also that you can keep this in mind, that the distance traveled and the closeness factor are one possible criteria. This is not the only criteria that we might use in deciding the layout of a given facility. This is one of the tools that we can use as operations managers in helping us to make the decision, and they keep repeating this over and over. All the techniques we discuss, all the methods we introduce, they are there to help us make a decision. They do not make the decision on our behalf. In the end, managers make the decisions. All right. So we saw earlier that in order to complete a layout of a facility, we need to gather appropriate information in terms of closeness factors or the importance of the proximity of different units or different departments. And in addition to that, we get the distances, and from that we generate a block plan, or a, that shows the relative position, the relative location of each department versus others. The evaluation criteria between different block plans, so based on the proximity, based on the weights or the closeness factors and the distances, we calculate a score. We calculate a total score for the proposed block plans or for the various alternative block plans, and we decide on which of those plans to take. The rule of thumb is that we take the block plan that has the lowest total score. All right. And the remaining question was, once we decide on the block plan for the facility as a whole, then we can do a detailed layout design by looking within each department. Then once I decide within each department might be actually divided into several units. Then we might look at the design of each unit, and we cascade like that in that order until we have a complete setup, a complete layout of the entire facility with all of its units and its departments and work cells and work units and all that stuff. That is essentially what we discussed earlier. Okay, now for the practice exercise. Okay. The practice exercise, here it is. Okay, we are in week 10. We have the following example. It says, a company evaluates its machine shop's current layout. They have the current layout. The figures below shows the current layout. And the table shows the closeness factors between the departments. Safety and health regulations require departments E and F to remain at their current locations. So therefore we have, this is the current layout. E and F are required to stay where they are. And the question is to, first of all, come up with a new plan using trial and error to find a better layout. So we have a current layout. We will try to come up with an alternative layout that can give us a better, maybe that could be a better plan. And we want to find out if the current layout or the proposed layout is your layout better than the current layout in terms of obviously the WD score. So here there are two things. We first need to find a better layout or a proposed, okay, layout or plan. How are we going to do that? Well, we have for E and F, we are told that these must remain where they are. Okay. So E and F must remain here. This is by virtue of the problem. So we need now to decide where to locate the others. Okay, where should we put all of the other departments? As I mentioned earlier, okay, one way to do this is really to, again, because this is by trial and error, this is a heuristic. Heuristic means it's not necessarily the optimal solution that we can have. If I have E and F, I can actually use those as maybe a point of reference and maybe determine from the closeness factors table what I should put in each one of these slots. So for instance, what do you suggest? What do you propose? What do you think we should put in each one of these? Any ideas? Hello? Any thoughts? All right, no reaction whatsoever. Okay, as I said earlier, we look at the closeness factors. So for instance, when I look at the highest ones, those indicate that those departments should be as close to each other as possible. So I look at this. The highest values I can find, 9, means A must be close to E, and C should be very close to F. So when I look at A, all right, to be close to E, it could either be here or it could be here. These are the closest slots to E. I could either put A here or put A here. Where should we put it? Because I look now at the other one. C has, you know, a closeness score of 9 to F. So therefore C should either be here or here. Okay. And therefore between, you know, so C should either be here or here. We need to decide what should we put here. Is it better to put A or C in this block? If I put C here, it's close to F, but what do you notice in the closeness table? The closeness factor of C to E is very high. is also 8. So if we can put C in a place where it is close to both E and F, that would be the best location. And therefore, C must be here because this is the location where it is closest to E and F at the same time, which means it cannot be here. And therefore, we should put A here, since A also must be close to E. This is one thing. Now, we have B and D left. We look at the closeness factors. The closeness factor between A and B is very high. So, if possible, put A or B as close as possible to A. The closest to A is right here, is B. Which means that for the last slot, the last location, this is where D goes. Okay, so you see what we did? All we did is we used our understanding of the closeness factors. The higher the score, the closer they should be to each other. So you see that the first thing we did was I looked at the highest ones, E and F, E with A and F with C. Which means that, and then I said A could either be here or here, C could either be here or here. In the middle location, which should we put in there? A or C? It turns out that C, because it also has a high closeness factor to E, this is the best location for C. And that leaves this location for A. So this is our proposed layout. Is this clear?
Doctor?
Yes.
Could you please repeat this?
Yeah, okay. The way we do this is I started first of all with the fact that E and F cannot be changed. How do I know that? It actually says here. E and F remain at their locations. So E and F are not going to change. Since E is here and F here, that's where they will stay. E and F will stay in here. The question now is, where should I put the other departments, A, B, C, D? The way to go about this is to look at the closeness factors. I look at the table, look at the highest values, because higher value means that those departments should be close to each other. Theoretically, they should be close to each other, as close to each other as possible. Okay. So here I find that 9, and there is a 9 also. So A should be close to E, should be next to E if possible. What does that mean? It means that A, this is E, so A should either be here or here. Either here or here. This is the closest to E. The other highest factor is here, 9, which is between C and F. So, since F is fixed, that means C should either be in this location or in this location. These are the closest to F. All right. So now here I have to choose either A or C, which is better. Well, it's obviously C, because C needs to be close to both E and F, and this is the best location for it to be close to E and F. So that's why we decided to keep C here. This makes sure that C is closest to E and closest to F. Why? Because it has high closeness factors with F and with E. When you look at department C, the closest factor is high with E and high with F. This is therefore a very good location for C, because it's the closest to both of them, E and F. Which means that A must be here, because A has to be close to E. You see, A has a high closeness factor with E, so therefore if A cannot be in this square, then it must be in this one. This is the closest remaining square to E. So now I have A and C chosen. Between B and D, I can see that B has a high closeness factor with A, 8. Therefore, B must be close to A. The closest to A is this square, so I put B in here because it's right next to A. Which means that the last one, the left, is, well, that's where we're gonna put D. Okay, so that's what we said. It's like by trial and error. Okay, the only way to do this for now is by trial and error. We're gonna, that's, and with some logic, some reasoning by using the closeness factors, and we try to say if it has a high closeness factor, then it should be close to it, should be near it. Okay, that is the idea. So now we have a proposed plan and we have a current plan, or current layout and proposed layout. We need to decide or to choose between the two layouts. We need to select between the two, which is better. Okay, and we'll do that obviously using this table of the we're going to calculate the WD, the distance for both of them. Now for this table, we're going to insert it here. Okay, so we need one column for the pairs, one for the factors, one for the distance in the current plan, one for the WD, and then one for this is the proposed plan, and then for the second one. So we have a total of 6 columns. For the rows, okay, we're gonna see. So we have the pair, the closeness factor, which is W, distance for the current layout, then W times D for the current layout, okay, then distance for the proposed layout, and WD for the proposed layout. Okay, this is what we should do. How do I generate the pairs? As I mentioned earlier, the best thing to do that is from the closeness table, because the table will tell us which ones are relevant and which ones are not. So for instance, I do not have to put AD because it's irrelevant. There is no closeness factor. So what are the pairs? I have A and B. That's one pair. Then we have A, C. That's another pair. Then we have A, E. You see, D is irrelevant. There's nothing in there, so I just put the pair A, E. And AF, you can see there is a value here, so AF. For B, the only one that's relevant is department D. You see, for C, E, and F, it's irrelevant. It's only one pair, which is B and D. So B, D. Then for C, D is irrelevant. There's nothing. Then it's E and F. So we're going to have pairing C with E and C with F. Okay, we're going to need some more rows. Okay. So C, we're done. C. Okay, now what else do we have? For D, we only have D with F and E with F. So D with F and E with F. D paired with F and E paired with F. Okay. We don't need this last one. And we're gonna have the total for the all right. The weights are directly from the table. So AB, the weight is 3, so 8395. BD, BD, the weight is 3. CE 8 and CF is 9, so 8 and 9. DF is 3 and EF is 3, so those are the closeness factors. We just copied this from the table. Now for the distances, okay? Let's put it here so that we can see it in front of us. Okay, this is the current plan. What is the distance from A to B?
2.
2, correct. A to B, just 1, 2, correct. From A to C?
Only 1.
Only 1, it's 1 trip. From A to E?
1 also.
1 as well. Then from A to F?
3.
3. 1, 2, 3. So it's the number of movements or trips. B to D. This is B and this is D. So
2.
2. C to E. So 1, 2. C to F.
2.
2. Correct. 1, 2. D to F, they're adjacent, so therefore only 1. Very good. 1 movement. And finally, E to F, we have from E to F is 2. Exactly. Which means that we can therefore calculate the WD scores for the current plan, and it's simply the multiplication of the score or the weight by the distance. So 8 times 2, 3 times 1, 3 times 1, 9 times 1, 5 times 3, okay, W times D, 5 times 3, 3 times 2, 8 times 2, 9 times 2, which is 18, 3 times 1, and finally 3 times 2, which is 6. All right. So it's very straightforward. Once I have the weights and the distances, it's just a multiplication. So this time this, and then it's like a sum product. The total is the sum of all of the WD scores for the individual pairs. So 16 plus 3 plus 9 plus 15 plus 6 plus 16 plus 18 plus 3 plus 6, which is equal to
92.
92. Okay, it's 92. So that's the current plan for the proposed layout. Again, let's put it here so that it's in front of us and determine the distances. So starting with the distance A, the pair AB, what is the distance in there?
1.
1, correct. A to B, it's only 1. A to C.
2.
2. A to E, they are adjacent.
1.
So therefore 1, good. And then A to F.
3.
3. Then B to D.
1.
1. They're right next to each other, adjacent. It's only 1 trip, 1 movement. From C to E. This is C. This is E, so therefore 1, correct. C to F, also 1. D to F,
Also
1 as well. And finally from E to F, because they are fixed, it's going to be the same thing as we had in the previous plan. It's therefore 2. And we do the same thing. So the weight multiplied by the distance. So in the first one, it's 8 times 1. 3 times the distance. So 3 times 2, which is 6. Weight, which is 9. Distance, which is 1. So 9. Weight, which is 5. Distance, which is 3. So 15. Weight, which is 3. Distance, which is 1. So 3 times 1, which is 3. Weight is 8. Distance is 1. So 8. Weight is 9. Distance is 1. Okay, the next one. 9. Distance is 1. So 9. Weight is 3. Distance is 1. So 3. And finally, the weight is 3. And distance is 2, which gives us 6. For a total of
67.
67. Okay, great. These are the total scores for the 2 plans. And therefore, which plan is better?
Proposed layout.
Correct. The proposed layout is better because, why is it better?
It has the lowest total.
Very good, because it has the lower total WD score. Correct. That's what we that's how we solve this. Now back to the original maybe question of the different plans. As you can see, there are many different plans for there are a lot of different combinations. Actually, having this assignment assigning 6 to 6, there are 36 possible layouts. Now, are we going to actually check every one of these 36? Generally, no. What if I'm interested in, if this is and by the way, the reason we are not looking for necessarily the best possible plan is, as I said earlier, because this could be just one of the criteria in the choice of the plan. Because if this was the only criteria, then we can certainly find the optimal allocation of these departments to different locations by solving an assignment problem like you did in operations research. Okay, but that's not the purpose or the objective of our discussion in this course. In this course, we want to remind you that all of these tools and techniques we learn are decision support systems. They help us in making the decisions. They don't necessarily make the decision for us. So is this the best possible plan? We don't know. Actually, we already have a case in point. When we developed this plan, we developed based on the the greedy approach, where we tried to starting from the closeness factor table, just make those that have the highest closeness score next to each other, and that will give us a good plan. It's not necessarily going to give us the best plan, and we already saw that in the example we did in the lecture earlier, where we used that same approach and tried to put all the ones that have the highest score next to each other. It doesn't necessarily work. And obviously the problem becomes more complex as I have more slots and more departments. So this is with only 6 departments, okay? Well, there are some companies that have maybe, instead of 6, they might have 12 different departments, so they might have 10 or 20 different departments. So the problem becomes more and more complex. And for now, okay, as the question says here and as we have done in the lecture, it's trial and error, okay? Trial and error. But it's trial and error that, as I said, using this greedy approach can give you a pretty good, proposed layout, like the one we have here. And it does turn out to be better. And it turns out to be significantly better, actually. It's dropped from 92 down to 67. That's a drop of about 30% or 33%. That is a major, major improvement, okay? So are there any questions on this? Is this clear how we're getting these distances, how we're calculating the scores and all that stuff? Any questions on this? Any comments? Is this clear?
Doctor?
Yes, Manuel.
If we use these techniques to solve company problem, we should try all possible layouts?
Well, that's a very, very good question. I've already tried to address it. Well, if we are looking for the least distance, then in that case, you see, if that was the only criteria and I want to find the one that has the lowest score, then checking every single plan would not be the best approach. That would not be the best way to go about it. In that case, just solve the assignment problem using operations research techniques that you have learned in operations research. Formulate the assignment problem where you have like 6 slots, for example, here, and I have 6 departments. And, you have a an integer decision variable, which is, for instance, I would say x, E1 or or Xij is the, 1 if the department is assigned to that location, 0 otherwise. And we can solve that to optimality. Why don't we do that in a lot of cases? Because, as I said, in a lot of cases, this distance or the total score that we are minimizing could be just one factor in the choice of the plan that we have. Okay, it could be just one of the factors that we are considering. There could be some other factors. Okay. The other thing is that in a lot of cases, and you actually already see this even from the way the questions are asked, okay, usually that I have a current layout and I'm thinking of another one. So I maybe come up with another one and try to decide, is this better than the one we currently have or not? So generally speaking, this is like part of what we call the continuous improvement. We are trying to continuously improve as opposed to drastically come up with something that is totally different. So to answer your question, if I want to find the one with the absolute lowest score, then the best way to do that is to solve an assignment problem. Because doing this for every possible plan, well, as I already said, there are 36 different plans here. Actually, I think, well, no, not 36, but like 6 factorial. It's actually about, there's a significant number, okay? And that is a very, very large number of different plans. We cannot actually go over every one of them. That will be a waste of time. Okay. So in this context, we're using these only if I already have like plans that we generate as we did here, using some heuristic like the greedy approach. If I'm interested in the best possible plan, then the best way to go about that is to solve an assignment problem. Very good question, Maimon. It's good. I hope I gave you a very good answer as well. Did this answer your question?
Yes, thank you.
Okay. All right. Are there any other questions? Any other comments? All right. So let's conclude by again doing this in Excel. Okay, just to refresh your memories on how we're actually accomplishing this in Excel. It's again, it's very, very straightforward application even in Excel. So let's do this. Okay. Obviously, the data is not changed. What we need to change are the calculations. Very straightforward calculation. It's simply the weight multiplied by the distance. And the beauty of Excel, just write it once and copy it down. The total is simply the sum of all of the values. So if I sum all of these, we get exactly 92. That's what we already obtained earlier. Okay. Also, the good thing about this is that, you know, suppose that I actually had some of these weights incorrectly entered. Okay. If in this case, all I need to do is just change the weight, and I'll end up with the new scores without having to redo everything. So weight multiplied by the distance, and we'll copy this to all of the different combination of the pairs, and we sum over all of the pair combinations, and indeed we get 67. That's what the value that we obtained. Okay, very straightforward, very simple. And that, my friends, is the conclusion of today's wonderful story. So do you have any questions, okay, about this? Is this making sense? Any questions on this? Clear? Okay. If there are no questions, that's all I have for today. Okay, so we went over the solution to the practice exercise. I showed you how to do this in Excel. There is not much left to talk about. If you have any questions, as usual, you can always ask me or Dr. Riza, and we'll be more than happy to answer you. Okay, clear, Doctor. Thanks. Well, thanks, Dave. I'm glad that it is clear. All right, so then if everything is clear, and it seems to be the case, then we'll stop there, and we'll see you, inshallah, next week.